Welcome to free response question numero dos, or FRQ2, as the kids on the street say. No one says that. This is a problem where a calculator is allowed, and we're just going to get right to it. Imagine a biologist conducting research on a particular species of bacteria in a laboratory setting. So close your eyes and imagine that. In 2018, where T is 5, time is 5, the biologist observes 200 bacteria. By 2024, this year, where T is 11, the population had grown to 800 bacteria. The population of this bacteria species can be described by the function B given by an exponential function, where B of T represents the number of bacteria in year T. Usually when you're dealing with some type of growth or a population growth, it is going to be exponential, and so that should not come as a shock here in any way whatsoever. So, A and B are just some numbers we need to figure out. B of T is the total population after T amount of time. So use the given data to create two equations for finding the constants A and B in the expression B of T. So what part I is asking for is come up with two equations, like a system of equations. Well, in order for me to come up with the equations, I have to take some of this information that I have right here. So what I do have is that when T is 5, I have a population of 200. So that gives me the coordinate 5, 200. So using that information where 5 represents T and 200 represents B of T, I can come up with the equation. Instead of B of T equals AB to the T, I can come up with the equation where I substitute B of T with 200, A is I don't know, B is I don't know, and T can be 5. So that's one equation. Now, if you're like, oh, I think I know what's going to happen next, you're probably right. We have another coordinate that's 11 and matches up with 800. So I have 11, 800, and that gives me the equation, replace B of T with 800, A is I don't know, B is I don't know, and replace T with 11. So what we have here is a system of equations, and I can use that system of equations to help me solve for A or B, which is something that I absolutely don't want to do in this situation, but I could if I really wanted to. Now, what I'm going to do instead, since this is a calculator problem, I'm allowed to use my calculator. I'm going to do 2 by using exponential regression. Now, exponential regression is something that you could do in your calculator that gives you something in the form A times B to the T. So I can run to my calculator, I can type all this information in, it's going to spit out some probably gross numbers, but I'll be all right, and then we'll write that down once we're done. Be right back. So exponential is going to start out just like any regular regression problem. So we go to Stat, Edit, and we type in our points. We had 5 matching up with 200. We had 8 matching up with, 11 matching up with 800. Got those backwards. Could have been dangerous. Now, what we do when we're done with our 2 points, and that's all we have, is we go to Stat, Calc, all the way down, I think, to 0 is exponential regression. Yep. So 0 is exponential regression. Now, since I'm going back and forth from my notes to a calculator, I'm not going to store this regression equation because it won't work for me. It'll disappear by the time I go back the way that I'm recording this video. So I'm going to ignore that. I'm going to hit calculate, and it gives me something awfully gross. Unfortunately, it's not 63. It's 62.996 and 1.2599, so 1.260 is going to be my guy. So I'm going to go back and use that information right there to come up with my equation. All right, so we ended up with y equals blah, blah, blah to the x. Well, I'm not going to write out y equals. I'm going to write out b of t equals, it was 62.996 times 1.260 to the t power. Now, I could have come up with those numbers using this method, but you could see why I wouldn't want to use substitution or elimination or whatever god-awful mess it would be. Log would be involved probably. I don't want to deal with that, so I'm not going to deal with that. Okay? All right. Part 2. Same question. Utilize the provided data to determine the average rate of change of the number of bacteria measured in bacteria per year from 5 to 11 years. Well, fortunately, we're given 5 to 11 years, so that makes life easier. Express your answer as a decimal approximation and show the computations that lead to your answer. Normally, when you think average rate of change, you think f of b minus f of a over b minus a, right? Well, the same thing's going to happen here, except I'm going to use b's and t's. But I'm still going to use little b's and little a's. So this is the part that counts. That blue part doesn't count. I'm going to write out f, or b rather, of b minus capital B of a over b minus a. Okay, now I know what these are. These are going to be my B and my A, so you're going to be 5 and 11, but let's do 11 minus 5 in that order. Let's do 11 minus 5. I don't know why I would put it the other way. No. Yay. B of 11, I'll deal with in a second, minus B of 5. Now we know what those are. B of 11 was 800. Minus b of 5, we know is 200 over 6. So you become 600 over 6, which becomes 100. So this is going to be measured in bacteria per year. It's going to be an increase of 100 bacteria per year. Now, that's just the average rate of change. We already know very well from the previous problem that this is an exponential guy, so it's probably going to look something like that, but this is asking you to find what that is right there. Find the slope, and the slope is 100 bacteria per year. So, interesting problem. Use the average rate of change found in 1, which is 100, to estimate the number of bacteria for t equals 14 years. Show the work that leads to your answer. Well, we have 11 years, and 11 years is 800. So the work that I'm going to show is the fact that 14 is 3 more years more than 11, more, and I'm going to multiply that by 100. That's going to end up being 1,100 bacteria. So I didn't show a ton of work. I'm not sure what other, unless you want to describe or explain what's going on and say, I am adding 3 because that's 3 years after 2000, whatever. I'm always very paranoid where I like to show or write more than necessary. I don't know if they'd accept something like this. Maybe they would. I'm sure they would. But if you're always paranoid, just add more. Just make sure you don't make a mistake. The average rate of change found in I can be utilized to estimate the number of bacteria during year t for t is greater than 15 years. Will these estimates obtained using the average rate of change be less than or greater than the number of bacteria predicted by the model B during the year t? So, okay. Oh, and I only care about 15 to 25 years, not including 15. All right, so this is what I have to do. I have to compare what I got in part 2 of part A on the previous slide. And if you remember, that exponential function was b of t equals 62.996 times 1.260 to the t. That's my exponential guy. Now, my linear guy can be found by saying, all right, well, my slope is 100. So y equals 100x. I don't know what my y-intercept is, but if I take one of these points up here, like the point that I just came up with, what was that? 1010. If I take a point like that and plug it in, I get 1010 equals 100 times 14 plus b, you become 100,000 or 1010 equals 1400 minus 1400 minus 1400. B is equal to negative 300. So the linear equation that I get that is supposed to do a good job predicting data after 15 years is going to be y equals 100x minus 300. So what I need to do is I need to graph u and I need to graph u on the same graph. What I want to do is I want to compare what's going on between 15 and 25 and see which one, or see if the average rate of change, see if the linear one is less than or greater than. So again, I'm going to get a picture like this, right? And I don't know what my line is going to look like, but I need to find out, is my line greater than the exponential guy or is my line less than the exponential guy? And that'll be my answer to that. So let's run back to our calculator and figure that out. Okay, so let's graph them both. Like I said before, it sure would have been nice if I stored the exponential function, but since I'm going back and forth to my thing in the calculator, it deletes everything automatically. If you were able to store it, good. It would look like this, 62.996. And of course, if you did store it, it's going to give you a whole lot more points, but oh well. Times 1.260 to the t, so to the x. That's my exponential function. It's going to show up in blue. My y function is going to be y equals, or not my y, my linear is 100x minus 300. If I hit graph, I'm not near at all where I want to be. Okay, now what I care about, first off, is a window between 15 and 25. First, I need to see where these intersect. So I'm going to zoom out until I can see where they intersect. Not yet. Zoom out again to see where they intersect. That might do it. Okay, now it intersects like way up here. So what I'm going to do is I'm going to set my window to 15 to 25 because that's what I care about for my x values. And why don't we change my y min to 50 and just see what happens. Well, that's unfortunate. Let's zoom out again. Enter. Okay. So let's change my window to, let's do 100. Let's change this again from 15 to 25. And that's again unfortunate. So let's zoom out one more time because I'm trying to get the y's. All right. So what is this? What is this x value? Oh, the x value, hold on. The y value, okay, so the intersection here happens at 196. Okay, so let me see. Where does it, okay, okay. Let's do this. Let's go up to 500. I think I got it. Let's go up to 500. And by the way, this is kind of like a good thing that this is happening, that I'm like testing stuff out. If you're like, zoom fit, that might be useful, but it's too late. Let's change this one last time, hopefully, please, Lord, to 15 to 25. Hit graph. And how is this still not working? Am I still too low? What if I made this 1,500? Just overdo it. Hey, so now I don't see my exponential function. So let's make this 1,000 to 2,500. So much troubleshooting. All right. So there's my linear equation. There's my exponential equation. You can tell by the colors, but this is between 15 and 25. My linear equation is underneath my exponential equation between 15 and 25, no matter what. So it took all of that for us to figure out that our average rate of change possibility is going to be less than the model that we predicted back in part A. So after all of that, that's our answer. So let's go back and do that. All right, so after all of that, if you gave up on the video, I don't blame you. But what we saw is this guy, where the linear graph is below the exponential graph. So the average rate of change is less. The average rate of change, that's two ofs. The average rate of change will be less than. And to explain why, ... we'll write it out over here, because the graph of our average rate of change formula is below the B of t formula. So not a lot of room to write all this stuff out, but I was able to make it work. Sloppy, but I was able to make it work. So let's close this puppy out. Imagine, same problem. For which t value, t equals 8 or t equals 20, should the biologist have more confidence when using the model of B? Give a reason. All right, well, the model that we have is a model based off of numbers between 5 and 11. So it's going to be clear that t equals 8, okay, would be a better prediction because 8 lies in between our given t values of t equals 5 and t equals 11. Since t equals 20 is much greater than t equals 11 was the biggest one, our model may not show as much accuracy. Which makes sense. If you're going to predict something between 5 and 11, or predict something based off of 5 and 11, 8's literally right in the middle of it. 8's in the middle. So you wouldn't say, oh, yeah, I'm more likely to guess what's going to happen for 20 than for 8 because, you could graph these two and you can at least estimate what's going to happen in between. It's hard to estimate what's going to happen at t equals 20 because 20 is way down the road. So we did it. We did free response question number 2. Lots to do in this, lots to handle, but hey, I'm happy for us. I'm proud of you. So as always, I hope this helps.